So last class we discussed about the Lorentz force, and in this class we'll discuss about the magnetic force on a current carrying placed in a uniform magnetic field. So uh, what we learned in the Lorentz force, that when the charge particle is moving with some velocity, uh, which is placed in a certain angle with the magnetic field, and it will experience a force in this upward direction. So now in this case, see, this is a conductor, this one is a conductor, and I current is passing through this conductor. So as you know that as the I current is passing through this conductor, that means more electrons are more huge number of electrons are moving through these conductors. Okay, so as the huge number of moving electron is also a charged particle, as it is moving in this through this conductor, and so how much force this conductor will experience, that we are going to find out. So that is why the name of the topic is the magnetic force on a current carrying conductor placed in a uniform magnetic field. So this is the uniform magnetic field B, and I said this is the current flowing in this direction, and the force is actually in this direction, like this way. That you have to find out the actual, or how they are related. Actual formula will come from here, that we are going to find out. So first we write the heading here. So magnetic force on a so this is the heading. Now the total length of this conductor is L. So you have taken a very small amount of length, that is dl here. Dl is very small length. So we'll calculate the magnetic force. This is force due to this small length, and then we'll do integration so that we can find out the total force applying on this in this conductor. Okay. So we'll take, this is the length, I is the length of the conductor. So L is the length of the conductor. L is equal to length of the conductor. Relate. And I current is placed in uniform magnetic field. So I is equal to current. B is equal to magnetic field, you say, you know. Magnetic field. And here we also take that n is equal to, small n is equal to number of free electrons per unit volume. These are all so number of free electrons per unit volume. Okay. Now, how much force will be applied on one electron? So you can write magnetic Lorentz force on one electron. Force acting on one electron, acting on one electron. So what is the formula? We learned Fm is equal to, we'll take a small f, because it is only you're going to find out only for small on a single electron, that is why minus E B cross B. Okay, acting perpendicular to the plane of, this is acting perpendicular like this way. So you can write acting perpendicular to the plane of V vector and B vector. So this is the thing. So now we'll consider a small element. This is called dl is the small element. So dl is equal to, dl is small element of length. Now, what is the volume of this portion? One more thing I also forgot to tell, that this A is the area of cross section. Okay. So if A is the area of cross section, this is also A. So what is the volume of this portion? With a small dl is a small length, small element of length. So volume of that small element. So volume of that small element will be how much? Will be, this is dl into area of cross section into length. So A into dl. So this is the volume. Now the question is that how much electrons will be, how many electrons will be there in that small element. So already it is written here that the number of free electrons per unit volume n. Okay, so multiply with the volume, you will get the number. So number of electrons in the element will be n into this volume, A into dl. So this is the number. Now, so magnetic force experienced by this element. So magnetic force experienced by one electron was this Fm, and the magnetic force experienced by this much of electron will be completely multiplied with this one. So you can write N A dl into Fm. So you have to put a vector formula here, this vector symbol. So vector here. So this one. Now we'll do some adjustment with this one. So you can calculate. So is equal to N A dl. You put a bracket here. Then Fm is equal to minus E, then V vector cross B vector. You can see also. Now we take E in this side. So minus N A dl, then V vector cross V vector. Okay. So this we got from this thing. Now drift velocity. Drift velocity V vector is equal to minus dl by dt. So already you know that the electrons is moving in the opposite direction of the, so that is why so V is equal to minus dl by dt. Okay, now we'll put the value of V in this equations. So this is separate, I can put a bracket here. So input the value of V vector in this equation, then we'll find out what are the things. So now the magnetic force experienced by the element is on this one. You can write as dFm. See, this one is capital F. So also dFm, like this way. So you can write here from this, putting the value of V in this equation. So what will write? And also one more thing that you can write here. So A into, if you take this E outside from here, if you take this E outside, so A N A E N A D dl into E will become the complete charge. So this is the number of electrons into electrons. So this is charge. So you can write also here. So N A dl into E is equal to dq. So there is a charge. So now I'll put all the value here. So you can get dFm vector is equal to dq, and then dl vector by dt cross b vector. So we'll get dq by dt, and then dl into b vector. Okay, dl vector into b vector. See, this dt has come to here. So what is dq by dt? dq by dt is I. Okay, current. So dFm vector is equal to dq by dt. So you can write dq by dt means I, current, and then we'll get dl vector into b vector. So this is your formula. So now you have to put this one into a box. So this is the formula. Okay. Now, if you want to find out the total force, what is the integration of? So if we have to do integration for this one, so integration of so if Fm is equal to Fm force is equal to integration of dFm. So integration of dl will come how much? dl will come L. Okay. So what will happen? You can write I. Then this cross product. So you can write dlb sine theta. So dl will integrate into come to L. So you can write I. Then integration dl vector cross b vector. Okay. So also you can write I in bracket L vector cos b vector. Okay, from here. So this is separately I'm doing. Space is very less. So that is why you can write Fm is equal to I. Then you can write BL sine theta. Okay, so this is the formula. Another formula after integration, this one total force. So to remember, you can remember in this way, Fm is equal to Bill sine theta, BIL Bill sine theta. Okay, so this is the thing, and next class we'll continue with the Fleming's left hand rule. So you can find out the direction of the current carrying conductor placed in the magnetic field using Fleming's left hand rule. Okay, so today is up to this. So thank you very much.